Greetings, everyone. I'll try to make this quick. Just wanted to do a speed run through test 2 here real quick. So this was problem 1. Basically, you just need to recognize here that x1 and y2 rather, are just e1 acting on x and e2 acting on y. You remember we talked about the dual basis picking off components? So just putting that into practice, and then this is just using the definition of the tensor product. So lo and behold, we have that f is actually e1 tensor e2 minus e2 tensor e1, or if you like, the wedge product of e1 and e2. Now, that was problem 1. Now, problem 2, most of you guys got this right. And people who got it wrong, it was just like you just got sloppy. At some point, you changed this y into a y squared or something. And then, like, the larger point to notice here is there's no need to calculate the 3-form pullback, because we already know there is no non-trivial 3-form on R2. So we pull back to R2, it's automatically 0. So there is that. Now, problem 3. I like this question. It's not particularly, tricky. Pretty much just need to recognize that when we take the wedge product of the work forms, we get the flux form of the cross product. And when we take the wedge product of the work form with the flux form, we end up with a dot product of the vectors involved. This one here, again, you follow instructions, not that complicated. Just exterior derivative, recognize that the components here of the gradient are 2x, z, and y, and the exterior derivative of the work form, we recognize that there is just a y component of 2z, and of course the meaning is that's the curl of the vector field f, because we have this general identity, so we can, by comparison, see that that's the curl. And then, of course, down here, the exterior derivative of a 2-form, of a flux form, ends up giving us the divergence of the vector field times dx wedge dy wedge dz, which then implies, of course, the divergence is the coefficient of dx wedge dy wedge dz. This is, of course, a very, very silly way to calculate the divergence. Very, very clunky, but I'm illustrating a larger idea, which is, of course, that the exterior calculus reproduces vector calculus. Now, problem 5, I would hope you guys could get if I asked it again on the final. We did this in class. It was a homework problem as well. We just need to adopt the notation which is suitable. I use the multi-index notation. The key point here, of course, is that we have to do the product rule at one point, and we have to permute the differential dxk with dxi. There being p-fold differentials here, it costs us a -1 to the p factor, which we see in the product rule. This one here was a twist. This is a new problem. I just thought of this for you guys this semester. And so basically the idea here was I gave you a very particular property for this differential. Like the differential of omega fg was f times the differential of omega g. Well, that's not usually the case, because usually we have a product rule, and so if you compare the product rule to what was given, it implies that a particular thing in the product rule is 0, which is tantamount to saying that the gradient and gradient cross the vector g is 0. And then for the other one, similarly, you end up with the gradient dot the g. It has to be 0 if you look at it. All right, so this is just kind of a next level problem involving the product rule. Sometimes I ask you guys to prove the product rule. That time I was trying to get you guys to use it. I don't think anybody really fully understood that problem. I had some people who did things that were less wrong than others, but I don't think you guys quite understood the problem, the previous problem. Maybe it's my fault, wording-wise, whatever, but this is the Tesseract problem. We kind of worked through this in class before. I was trying to make it work out to, to 47, but I failed. The mistake that all of you made was you somehow dropped the x on 84. Like, anybody who got this wrong, but almost right, it's because you changed 84x to 84 for some reason. Anyway, yeah, that one. Problem 8 and 9, here we have problem 8 solution. If you look at omega as m dx plus n dy, omega wedge omega is 0, the omega is 0, so that's automatically true because every 3-form on R2 is 0. And as such, that means that one form satisfies the necessary condition for for omega to be the defining one form of a distribution of codimension 1, which happens to be a set of curves, a foliation of the plane by curves here. And as such, that means that there has to be some h such that h times omega is df for something, because we can write our curves in the foliation as level curves, and then of course the exterior derivative, well, df is 0 along the level curve, right, which then by process of the geometry here means that omega has to be a multiple of omega has to match df, which is kind of just a fancy way of saying that there's some function h that when I multiply it by omega, it makes it into exact. So this is essentially Pfaff's theorem, which says that any inexact differential equation can be made exact simply by multiplying by an appropriate integrating factor. And the bonus question there was simply an invitation for you to use the integrating factor method to solve a differential equation, actually. So this is Calc 2, because there we study the linear differential equation, and that's what this was. If you just do this, its linear integrating factor is x squared, boppity boppity, it's exact, you can solve it. Flip side, you could also just multiply the given one by x, and if you do that, it makes it exact. So like, starting with the given differential equation in the bonus statement up here, if you just take this gadget right here and multiply by x, it becomes exact. So actually x is an integrating factor there. Anyway, so there's that. I think everybody who tried to do that one, problem 8, did better. People who tried to do 9 just did not succeed. You guys have to think harder about these things. Closed. First of all, you need to calculate more carefully, because a lot of people decided it wasn't closed because they miscalculated. It is closed. You need to do the calculus. So, like, if I calculate these partial derivatives, I get this, I get that, and it does work out to 0 if you're careful. So, in fact, omega is closed. And to check exactness, well, that's tricky. But basically, the idea of this example is that it's simply a slight deformation. Well, it's a slight shift, in some sense, off the differential of the angle. So like the differential of the angle, we talked about that in class. It's minus y dx plus x dy over x squared plus y squared. This integrates to 2 pi, of course, which underlies the fact that the cohomology of the punctured plane, or the circle, if you prefer, is non-trivial, because there exists this closed form which is not exact. And so that closed form which is not exact, I have just added the differential of 1/2 natural log of x squared plus y squared to that. And so that thing integrates to 0, because it's both closed and exact. But the d theta, of course, integrates to 2 pi, which shows you that the omega is not exact, because it integrates to 2 pi. If it was exact, it would integrate to 0 around the unit circle. So, in summary, if in doubt about a form in the plane, right, maybe try integrating around the unit circle, see what happens. Now, I didn't show you the details of that calculation, but they're pretty standard, right? You just put x equals to cosine t, y equals to sine t, then you calculate, dx, dy, plug it all in, work it out. All right, now we're getting into the funny part. So I have, now this one's hard. This one's hard, no doubt, no doubt. All right, so a couple things. All right. Well, I think I'll talk about this one now. So, yeah, find an A that exterior differentiates to phi b, where your b is essentially the inverse square law, right? This is, if you write it in sphericals, it's rho hat over rho squared, actually. Okay, well, we'll come back to that in a second. Finally, this is the last problem. And I think you guys got this. Some of you got this. And most of you got this. One of you got all but the last step. Just look at it. Oh, we've got A dot D plus B dot C. Yay. So what this means then, if you sort through the bonus part, is that upsilon wedge upsilon b upsilon ab wedge upsilon ba ends up giving us, of course, the length of upsilon squared by the previous work, and on the flip side, that means then by comparison that the Hodge dual of upsilon AB is upsilon BA. So it flippity flops the A and the B, forming the 2 form, which is kind of cool. That's a little bit different than the Minkowski space version of that, where there's also like a sign difference. All right, so let's talk about that pesky magnetic potential problem here. So this is the solution that my notes that I told you guys to look at, the monopole notes, it starts with this, which I think is taken from Nakahara's book. And then I work out from there that in fact, it in fact does give you a 1 form whose exterior derivative is the inverse square law. But that's great, but like how on earth would you find that, And I think I found a plausible path. Let me show it to you. This is not it. Oh. Yeah, sorry about that. But hey, I did calculate it, right? Yeah. See, I found it. There's the curvature right there. All right. Anyway, so I will try to look at your revised version 10s here sometime soon. Let me just get to the point here. I can't take too long here. Benjamin's waiting to watch Knight Rider, and I told him 10 minutes. We're already 11 minutes, 30 seconds in, so I'm getting in trouble here pretty soon. But anyway, so this is the magnetic field, the inverse square law. So it occurred to me, this is a spherical problem. I should try to work it in spherical coordinates. So what I did was I looked at the flux form. I thought, hey, you know what? We could write the flux form in the spherical frame. In the spherical frame, the flux form, it's going to trade a rho hat vector field for a theta 2 wedge theta 3. Now here, the rho hat, phi hat, theta hat, that's the spherical frame. The coframe, theta 1, theta 2, theta 3, it turns out it has to be rho d phi and then rho sine phi d theta. These are the covectors which are dual to these guys. All right, and I suppose I could derive that, but let me stick on point here. So this is going to, by definition, be that. And then if I put in what the spherical frame is, you see, well, that gives me a theta 2 is like rho d phi, and theta 3 is rho sine phi d theta, which gives me a d phi wedge d theta, and then this m sine phi business here. And then, well, that's actually kind of nice, because I can think about how to essentially integrate this, and in other words, how to look at this as the exterior derivative of a function, or 1 form rather. And so I started by going, well, sine phi d phi is really minus the exterior derivative of minus cosine phi, wedge d theta, and then I thought, oh, but that means, if I think about it, the exterior derivative of minus m cosine phi d theta is actually going to give me back this, and hence that. And so, lo and behold, I found the 1 form potential through that simple little argument right here. It's not that bad, really, if you have that idea. And so that gives me my 1 form potential is minus m cosine phi d theta. Now, then I'm like, but I want the Cartesian answer, right? So to get back to Cartesians, I remind myself, handy-dandy spherical coordinate transformations, and here's some, subsidiary relations. And then I plug that thing in here. So first of all, I came to terms with what d theta looks like in spherical. This is d theta in sphericals, which I worked out is 1 over secant squared times this business. Basically, this is coming from taking the exterior derivative of tangent theta is y over x. And then secant squared is 1 plus tangent squared, which gives me 1 plus y over x, y squared over x squared, which upon multiplication gives me this lovely minus y dx plus x dy over x squared plus y squared, which then, finally getting back to my 1 form I'm interested in here, this, I get that. All right. So just to clean it up, the 1 form potential that I have derived, notice that I've derived this starting with that simple argument on the previous page I showed you. I get this is my potential 1 form that will take the exterior derivative to give me back to the given b. And I checked it. I tried it. Plugged this thing into, I found the corresponding vector field, which is kind of obvious, right? Minus y times, y times z divided by square root of x squared plus y squared z squared times x squared plus y squared for like the x component. I took the curl of that thing, and I got b. It worked. It's legit. And so, um, you know, if one of you guys had done that on the previous test, I would have been like really, really impressed. But I thought there's a chance one of you would have had a spark of insight, and maybe some of you were closer to that than I realized. But that is a method to solve that problem. And I mean, it is a difficult question, right? How do we find a vector field whose curl is a given vector field? You know, how do we, given a particular vector field, how do we find another vector field whose curl is that given vector field? I do think that if you really meditate on the exterior derivative construction that we saw here, it does in some sense give a method, but this is something I only partly understand. So anyway, I just wanted to share this with you because I do think it is a plausible solution for number 11, which I just gave you guys all full credit for because I thought it was like nobody got really much closer to anybody else. So I figured I'd just give you guys all full credit for number 11. So my apologies if I should have taken points off, Anyway, see you guys tomorrow. Bye.